Hello and welcome back, dear students. Now we are going to discuss the second chapter of this drone pilot training course, and this chapter is going to be on basic principles of flight. In this chapter, we shall be discussing about all the governing laws, principles which are there that enables a flying machine to fly successfully, and we shall also look into the detail of how any drone can fly in the air. We will also cover some aspects of stability, and many topics are there which one should know if you want to learn about the aeronautics involved in this drone technology. So without further delay, let's delve into the topic. The fundamentals of flight and aerodynamics. Let us consider a case where you have an airplane and that airplane is flying at an altitude, let's say 3 kilometer high above the Earth's surface, and it is moving ahead with some forward velocity, which you could assume as 400 kilometer per hour. Now, that this airplane is flying at a fixed altitude and with this fixed velocity, there must be some physical phenomena which is happening over the wing of this aeroplane, and that is what we can call as the aerodynamics in action. This is the real life example of when we can say the aerodynamics is in full action, because over the wing the physical phenomena is happening in such a way that at any point on the wing, if you will anyhow measure the velocity of the airspeed or the pressure which is distributed over the wing, you will observe that at every point on the wing there is a unique value of velocity of the air and unique value of the pressure on the surface of the wing. This understanding of aerodynamics is very important for the overall understanding of flight. Aerodynamics is one of the four major disciplines which dictates the design of a flight. The other which are relevant subjects related to the successful design of a flight vehicle, flight mechanics, propulsion, and aircraft structures. Now, forces acting on an airplane during flight. We have considered the case where the airplane is flying at a fixed altitude and with a fixed velocity. You could think of there must be some forces which are responsible for this aircraft to move forward, and also the force which is enabling this airplane to hold at a fixed altitude, which we call it as lift. So let us understand one by one how many types of forces are acting on the aircraft during its flight and how those forces can be categorized. Basically, the force which acts on the airplane are of three types. It would be the aerodynamic force due to the flow of air over the body, or it could be a propulsive force due to the engine which is allowing it to move forward, or the third type of force could be the gravitational force. Now this aerodynamic force is further divided into two which acts on the airplane, and that is the aerodynamic lift force and the aerodynamic drag force. So we can see on the diagram where the four forces are shown on an airplane during the flight. The aerodynamic force acting are lift and drag, and the propulsive force is acting in the form of thrust, and the gravitational force is shown here to be acting in the form of weight of this aircraft body, and the direction of the weight force is vertically downwards towards the center of the earth. These forces during a steady level flight, when the altitude is constant and the velocity is fixed, that time these forces balances each other on the aircraft body, which means the lift can be said to be exactly equals to the weight when the altitude is fixed, and thrust is said to be exactly equals to the drag when the velocity is fixed. Now, let us try to answer to a very interesting question. How an aircraft or a drone can fly? For that, we must first consider a cross-section of a wing. You can consider we have a fixed-wing drone, let's say, or a fixed-wing aeroplane, where there is a wing. as a primary source of lift. If you will cut that wing, you will get a cross section which has a very special kind of profile, and that profile is referred as an aerofoil. By the side of the wing, if you will try to look the wing from it sideways, you will see the wing has a very special profile, and that profile is what we are calling here as a airfoil, which is a cross section of it. Now it is because of this very special kind of shape of an airfoil which is responsible for the creation of lift on the wing. Let us understand it into little detail. We can see on the screen, when the air flows and approaches the wing, what happens is this airfoil or a wing divides or cuts the air in such a way that the some mass of air flows on top surface of the wing, and some other mass of air passes from the bottom surface of the. It is due to the shape of this airfoil why the airflow on top surface of the wing has a higher velocity compared to the flow which is passing on the bottom surface. And the Bernoulli's theorem plays a very important role here. Bernoulli's theorem was defined by a Bernoulli for fluid mechanics, and he said that whenever there is a fluid flow, because air is a fluid, so when there is a fluid flow, if the fluid will experience the increase in velocity, there will be a decrease in the pressure. So what happens here is, the fluid, which is the air here, when the air is having a higher velocity on top surface of the wing, the pressure drops, and as a result, we have a low pressures on top surface of the wing and comparatively a higher pressure on the bottom surface of the wing. Now what happens? Anything wish to move from high pressure zone to a low pressure zone, and same happens with the airflow, because the wing, the bottom surface of the wing is in contact with the airflow that has a high pressure. That high pressure air wants to move up towards the low pressure region, which is on the top of the wing. Now because in between there is a wing and that high pressure air could not cross it, so in turn it exerts some pressure, some force on the wing. As a result, the wing lifts up in air. So this is how one can easily understand the reason how a fixed wing drone or an aircraft, you can say, can produce a lift and fly. So we can see the streamlines of air is shown here, which is bypassing over the wing, and how a fixed wing airplane is able to successfully takes off from the ground when the air has developed so much of lift on the surface of the wing. Bernoulli's principle, we have just discussed. What is the Bernoulli's principle? According to this principle, the fluid speed, when the fluid speed increases, the pressure decreases. So when air moves with a high velocity on top of the wing, then there is a decrease in the pressure. Let us discuss about the force vectors on an airfoil. Consider we have an airfoil and there is a flow of air which is taking place. It is important to understand the meaning of a chord here if we want to properly locate the lift force and drag force in their right direction on the aircraft. So this is a little technical, detailed schematic diagram where one can easily see how the lift force vector and the drag force is acting and their direction with respect to the relative. Chord line is shown here. This chord line is you can say is an imaginary line which you can get while joining the leading edge point of the airfoil with the trailing edge point of the airfoil. Now, when the relative air, when the free stream air approaches the airfoil or a wing, we can see it makes a certain angle with the chord line of the airfoil. So that angle is referred as angle of attack, and angle of attack existence is very important if one wishes to have a lift on the wing. If this angle of attack changes, the magnitude of the lift also changes, which is being developed by this wing. We can see when there was an angle of attack, there was a lift and drag force. The lift, we already know, this is aerodynamic force, and it always acts in a direction vertically upwards but perpendicular to the relative wind direction. And drag force can be defined as the force which is again a type of aerodynamic force acting parallel to the direction of the relative wind but opposite to the direction of forward motion of the aircraft. So I hope now it is very clear how the lift and drag force can be located with respect to the relative wind direction. This lift, which is acted on the wing, can be mathematically calculated, and the formula is on your screen. The lift formula is half rho v square s into c, air. Rho refers to a density of the air. It could be a density of the air which belongs to the altitude at which the aircraft is flying. Or for reference, you may also would like to use this value, a sea level value, which is 1.225 kilogram per meter cube. Now, V is a velocity of the free stream air. Free stream air is the same air which is approaching towards the aircraft when the aircraft is in its forward motion. So we call this free stream air as relative air also. So we not to get confused with this. Then we have in the formula capital S. Capital S refers to the wing area, the surface area of the wing, and we have the another term which is shear. Shear means lift coefficient. This lift coefficient depends upon the angle of attack. If angle of attack changes, the lift coefficient changes, and therefore in turn this lift on the wing changes. Let us now discuss the drone, which is of rotorcraft configuration. So far, what we had discussed was how a drone with a fixed wing can develop a lift. But the way these rotorcraft configuration develops a lift is somewhat in a different way. Let us understand. However, the principles are still same. The most common type of a drone which has a rotorcraft configuration is the quadcopter. And you can say in a quadcopter we have a 4 motors which are mounted on the frame, and those 4 motors has a 4 propeller blades, a kind of fan you can say, but they are of very special design, having a very high pressure ratio. That's why they are called as propeller rather than a fan. So those propeller blades are mounted on the 4 motors, and if you will look into the shape of this propeller blade, you will see that these propeller blades are actually a twisted airfoil throughout its span from root to the tip of the prop. And it converts this twisted airfoil or twisted kind of wing, converts the rotating power of the motor into the forward thrust to the drone. Now what happens? As the propeller spins around one time, the speed that the tip of the propeller will be having is faster than the inside portion of the propeller, because when it is rotating, the tip of the propeller travels a large distance as compared to the propeller's tip root. The propeller spins in such a way that it takes the air from the ambient atmosphere, and while rotating, it pushes that air downwards. Now, when the air is pushed downward from Newton's second and third law of motion, it results into a reaction force, and this force pushes the drone up in the air. Because you can understand from this Newton's second and third law. Second law tells us about the conservation of momentum. So when the propeller is rotating and it pushes the air downwards, it is actually changing the momentum of the air being pushed down. So because Newton's second law says that momentum should remain conserved, so as a result, there is a reaction force on the propeller blade, which as a result lifts the propeller upwards. You can also understand the development of thrust by this propeller from Newton's third law. Anything which is being pushed down gives an equal and opposite reaction, and that is what Newton's third law is all about. So this is how one can understand how the thrust, which is actually a lift being developed by the propeller, but in case of propeller, we call it as a thrust. The way we have just learned how a lift can be calculated, same way the drag can also be calculated, which is active on any flying object which is moving forward. Drag is the force which opposes the forward motion of any object. It acts on the fixed wing type of drone as well as on the rotorcraft type of drone also. The formula for calculating the drag is half rho v square s into cd. It appears almost similar to the formula of lift. However, we have here a drag coefficient in place of lift coefficient. Now, we shall discuss about the stability of the aircraft. So, what does this stability term means? Let me bring clarity in. Stability word basically refers to the tendency of any aircraft to return back to its equilibrium flying conditions after a disturbance, and this is done without the pilot's intervention or pilot's interference. In simple words, we can understand stability in this way. Suppose any aircraft is flying at some angle of attack. Let's say that angle of attack is 3 degrees, and suddenly what happened is a gust of air has come and it hits the aircraft from the down, and as a result what happens is his nose lifts up. So what happens is the angle of attack of the aircraft will get changed after being hit by a gust of air. Now let's say that angle of attack has shifted from 3 degree to, let's say, 6 degree, and this change in the angle of attack is not desirable for a pilot and for the air, because if that plane will continue its flight at this new angle of attack of 6 degree, it will definitely lose its flight, and it will also start rising up and start gaining the altitude. The altitude will no more be a fixed or a constant altitude, because we know lift is a function of angle of attack increases, lift increases. So if an aircraft designer has designed his aircraft in such a way that he has ensured a stability in the design, then because of this stability in the design, the aircraft will be capable enough to automatically return back to its equilibrium flying conditions. That means the angle of attack at which it was flying before it was hit by a gust of air. So gust of air was a kind of, we can say, a disturbance to the aircraft flight. So now we can appreciate this definition of the stability. Let us read again so that it settles down in our mind. Stability refers to the tendency of the aircraft to return back to its equilibrium after a disturbance. And this whole process of returning back or making an effort to return back to its equilibrium flying condition after disturbance is done by an aircraft without pilot's control or without pilot's intervention. This stability is very important for any aircraft because it maintains a very, very smooth, undisturbed flight. The stability can be of 3 types: longitudinal stability, directional stability, and lateral stability. Let us learn about each. So first, before understanding what is this longitudinal stability, let us understand the 3 different axes which passes through we can see on the screen we have an aircraft, and this aircraft which is shown here has 3 axes passing through it from the CG. So one axis can be seen which is passing from the nose of the aircraft to the tail, and that we call it as a longitudinal axis. Any motion about this longitudinal axis, the rotational motion, is referred as a rolling motion. Now the next axis is the axis which is passing from leftward tip of the wing to the rightward tip of the wing. And this axis is referred as lateral axis. Any rotational motion which this aircraft performs, which is about this lateral axis, is called as pitching motion of the aircraft. So we have a rolling motion, a motion about the longitudinal axis, and now we have a pitching motion, which is a motion about a lateral axis. So the third axis, which passes through this aircraft, is a vertical axis, and this vertical axis is exactly from top, passes from the aircraft to the in the downward direction. All these three axes joins together at 90 degrees at CG, and the motion which is performed by the aircraft about this vertical axis is referred as yawing motion. So we have a rolling motion, a pitching motion, and a yawing motion. Now we can easily understand what is longitudinal stability, what is directional stability, and what is lateral. When the aircraft is capable of killing the disturbance and has a tendency to return back to its equilibrium flying condition in the pitching plane, means when aircraft is capable of returning back to its original angle of attack after when the angle of attack has accidentally increased due to the gust, then we say that aircraft is longitudinally stable. So it can perform a pitching motion to return back, which is a motion about lateral axis. Now, what is directional stability? When the aircraft, let's say, somehow changes its direction due to the gust of air and the forward moving flight path is no more in this direction, now it is moved like this. So the aircraft can return back by generating a yawing moment, then we will say that aircraft is directionally stable. And the third, lateral stability, is a lateral stable aircraft can be said when the aircraft is capable of killing the bank angle and return back and align itself like this. So this means the stability in the roll can be said as the laterals. So this was all about the axis of the aircraft and the three stability of the aircraft. In longitudinal stability or in any stability, then there is a lot of importance of the CG of the location of the CG of an airplane or an egg. It is the location of the CG which affects the stability. For example, if you can see on your screen, the CG location, if it is ahead of the neutral point of the aircraft, then the aircraft will be longitudinally and statically stable. However, if this CG crosses the neutral point and moves forward to it, this aircraft will no more have a longitudinal stability. So the CG position affects the stability of the aircraft in various ways. Designer must take care that a CG should not overlap the neutral point or cross the neutral point. I mean, CG must always be ahead of the neutral. The more it is ahead, the more will be a stability in there. If it comes near to the neutral point, then the aircraft will become less stable. If it overlaps the neutral point, the aircraft will be neutrally stable. Neutrally stable means if the dust of air has hit the aircraft and which angle of attack has changed, let's say from 3 degree to 5 degree, and if the airplane is neutrally stable, the aircraft will continue its flight at a new angle of attack, which is 5 degree, and it will never make an effort to return back to 3 degree angle. So this is all about the effect of CG position on longitudinal stability of the aircraft. There are some important terminologies which one must know when they are operating their aircrafts or a drone. Takeoff. Takeoff, as we all know, it is the mode of flight in which an aircraft or a drone becomes airborne by developing the enough lift which allows it to leave the ground. So we have an image of a fixed wing drone shown here on the left hand side. It has become airborne and it has left the ground. We can say this mode of flight as a takeoff. In rotorcraft drone, rotorcraft drone is taking off from the ground in a vertically upward direction. However, your fixed wing drone, need some runway to leave the ground or to take off. So this is the basic difference between a fixed wing and a rotorcraft drone. Now the another mode of flight is a cruising flight. Cruising is the phase of aircraft flight that starts when the aircraft or a drone levels off after the climbing phase is over, and it lasts, this cruising phase of flight lasts until it begins to descend or approach for landing. Okay, at cruising, one more point should be kept in mind that aircraft is flying at a fixed height and at a fixed velocity. The next term related to the flight of the aircraft is a hovering. During the hovering flight, a rotorcraft drone maintains a very constant position in the airspace above the ground over a selected point. You can say usually a few feet above the ground. To hover, the drone will need to generate a net amount of thrust in an upward direction by all its rotors, and this net thrust must balance the weight of the drone. Then only the drone can hover. It is only the rotorcraft configuration drones that can hover. However, some fixed wing have this capability of vertical takeoff and landing, which are the hybrid fixed wing drones. They also have this hover ability, but the conventional fixed wing drone could not hover. The next important term is a landing. Landing is the mode of flight in which an aircraft or a drone lands on the ground. The rotorcraft drones need a landing pad. However, a fixed wing drones needs some landing strip to land successfully. The importance of a landing pad should not be missed. These landing pads are very important, and these must be used for a rotorcraft configuration drones because it provides a smooth and a solid surface for a safe landing. Sometimes you maybe as a drone pilot, when you are flying your rotorcraft drone in an area which is very fully crowded and so many people are around you, but if you have this landing pad placed in front of you, this gives a very clear impression to all the people that this is the landing zone and the takeoff zone, and they must not come near to it. So basically it helps a drone pilot to operate the drone safe. And not only this, because it gives a very smooth surface, so when the rotorcraft drones propeller rotates, it can invite a lot of dust and a lot of sand particles, and that which sometimes breaks or damage the propeller. So this landing pad is placed below the drone. The propeller blades are also very safe. Now the another term which is frequently used in aeronautics is maneuvering. Let us understand what this maneuvering means. Maneuvering words basically term refers to a different type of motions which an aircraft can perform. Now the maneuvers, the different types of maneuvers which a fixed wing drone is capable of performing is obviously different than the maneuvers which are performed by a rotorcraft. So we shall first look into a fixed wing drone maneuvers. One of the maneuvering of a fixed wing drone is a flat turning, a coordinated flat turn, where a fixed wing drone banks its wing and with some angle, and then it goes after taking a pack. It is with the help of ailerons, it is capable of taking a turn without losing the altitude. So this is one kind of maneuvering. The other maneuvering which is performed by the fixed wing drones is a pull-up maneuvering, where it can pull up and climbs to a higher altitude, and the another one is the pull down, with the aircraft pitches downward. So these are the maneuvers of a fixed wing. Now we shall discuss the maneuvers of the rotorcraft drones. Rotorcraft drones could not perform the maneuvers same as what a fixed wing drones are capable of. These rotorcraft drones performs a very simple maneuvers. They can just simply move forward. They can say pitches forward in the forward direction. They can come backward. They can go sideways. They can perform sideways motions. They cannot suddenly climb like a fixed wing drones. So if you will look at the configuration of a rotorcraft drone, say for an example of a quadcopter, we can see that the motors which are mounted on the frame of a quadcopter are mounted in such a way that the motor number 1, which can be seen in the image, rotates in the counterclockwise motion. However, the motor number 3, which is just adjacent to motor number 1, is moving in the clockwise direction. And then the motor number 2 moving in the counterclockwise direction, and the motor number 4 moving in the clockwise direction. So one should appreciate these unique rotations. These motors are diagonally rotating in the same direction, but the another pair, on the other hand, is rotating in a different direction. Have you ever thought, why is it so? Why they all are not rotating in the same direction? The reason is, if they all would rotate in the same direction, there will be a unbalanced torque on the body of this rotorcraft drone, and that will be in the direction equal and opposite to the direction of the rotation of the all 4 motors. So to balance, just for a stability in the design, a designer have very intelligently fixed the direction of rotation of these propellers. And this kind of configuration, the direction of rotation, not only helps this rotorcraft quadcopter type of drone is stable, but it also allows it to maneuver. What do I mean with this is, suppose if this rotorcraft drone wants to move forward, then this forward motion is possible when the rotating speed of motor number 2 and 4 is increased. So when 2 and 4 motors speeds up their RPM, it generates a little torque, and the rotorcraft drone moves forward. Same goes when it wants to return backward. The motor number 3 and 1 will rotate at a higher speed when the pilot wants to bring it backwards. And the another type of maneuvering which is associated with the rotorcraft roll is a yawing motion. The yawing motion. And yawing motion means changing its direction. This direction can be changed by changing the speed of the propellers of the diagonal motors. Speed of rotation of the diagonal motors means 1 and 2. If the speed of the diagonal motor is increased, the rotor will experience a yaw in the required direction. So this was all about how a rotorcraft load can perform different types of maneuvers and how this rotorcraft design is stable in itself. I hope this chapter has given you a lot of understanding with respect to not only what are the basic principles of flight, but it has given you a learning experience on what is the importance of stability and what are the different types of stability, how the stability can be ensured, and how this CG location affects the stability. With this, I would like to thank you all for being with me. Very soon, the next chapter will follow you. Thank you.